On the 27th of December 2004, astronomer Brian Gainsler stared at something that shouldn't have been possible. Data was flooding in from satellites across the solar system. Mars Odyssey, orbiting the red planet. Swift, freshly launched and designed to catch the universe's most powerful explosions. Resi, built to watch the Sunday. The European satellite Integral, scanning for gamma rays from black holes. Every single detector had been saturated by the same impossible flood of energy. Here's what made it truly strange. Swift wasn't even pointed toward whatever had caused this. The radiation had passed straight through the spacecraft's body, overwhelming its instruments anyway. From Saturn, Cassini had seen it. From deep in heliocentric orbit, Ulysses had recorded it. More than a dozen spacecraft, scattered across millions of miles, all struck by the same wave of energy at nearly the same moment. The source was pinpointed to SGR 1806-20. It sat 50,000 light-years away on the far side of the Milky Way, hidden behind dense clouds of interstellar dust. In 1/5 of a second, this object, no larger than a city, released more energy than our sun produces in 250,000 years. This was humanity's introduction to the full fury of a magnetar. The word magnetar sounds almost fictional, like something from science fiction. But these objects are terrifyingly real. They represent what happens when the universe takes one of its standard-issue neutron stars and turns the magnetic field up to levels that shouldn't exist. A neutron star already has a magnetic field 1,000,000,000,000 times stronger than Earth's. A magnetar has a field 1,000 times stronger than that. Think about that progression for a moment. Earth's magnetic field is what makes compass needles point north. It extends thousands of miles into space, protecting us from the solar wind. A typical neutron star's field is 1,000,000,000,000 times more powerful. And a magnetar's field is another 1,000-fold increase beyond even that inconceivable strength. Before 2004, astronomers knew magnetars existed. They'd been proposed back in 1992 by Robert Duncan and Christopher Thompson as an explanation for certain mysterious bursts of gamma rays coming from neutron stars. By the late 1990 seconds, the theory had been accepted. Scientists had identified a handful of these objects scattered through our galaxy and beyond. They understood, at least in theory, that magnetars possessed the strongest magnetic fields in the known universe. But understanding something in theory and witnessing its power firsthand are very different things. The December 27th event changed everything. It proved that magnetars weren't just extreme in their numbers in the sterile measurements of magnetic field strength recorded in scientific papers. They were extreme in their ability to reach across the void of space and touch us. The burst from SGR 1806-20 didn't just blind satellites. It partially ionized Earth's upper atmosphere. It made our planet's magnetic field ring like a bell. Fishermen in the Arctic saw a sudden aurora at the moment the wave hit. For a brief instant, the ionosphere went from night to day, all of this from 50,000 light-years away. If that magnetar had been closer, say, within 10 light-years of Earth, the blast would have stripped away our ozone layer and possibly triggered a mass extinction event. As of 2021, astronomers have confirmed 24 magnetars, with another 6 awaiting final verification. These are just the active ones, the magnetars currently producing detectable bursts and flares. Scientists estimate there may be 30 million inactive magnetars scattered throughout the Milky Way alone, ancient corpses whose magnetic fields have decayed, who've gone quiet after their brief, violent lives. The closest known magnetar to Earth is AXP 1e 1048-59, sitting about 9,000 light-years away in the constellation Carina. That's comforting in its way. Even the nearest of these monsters is far enough that we're safe from anything but the most extreme events. But that distance also means we're watching these objects from afar, trying to understand physics at extremes we could never recreate in our laboratories. studying a type of matter that exists nowhere else we know of. Magnetars don't last long, not by cosmic standards. Their intense magnetic fields decay after about 10,000 years, and when the field goes, so does their defining characteristic. They settle down into ordinary neutron stars, still dense beyond comprehension, still bizarre by any earthly standard, but no longer the magnetic monsters they once were. This short lifespan means magnetars are rare in the sky at any given moment. It also means that every magnetar we observe is, in cosmic terms, but here's what we need to understand to appreciate these objects. How does something the size of a city generate a magnetic field strong enough to warp the fabric of space-time itself? How does it form in the first place? What actually happens when one of these things cracks its surface in a starquake? And why, despite their awesome power, do they fade so quickly? To answer these questions, we need to start at the beginning. We need to understand the life and death of stars. Stars are born from clouds of gas and dust, collapsing under their own gravity until the pressure and temperature at their cores ignite nuclear fusion. For millions or billions of years, they shine, balanced between the inward crush of gravity and the outward push of radiation. Our sun is a medium-sized star, midway through a life that will last about 10 billion years. When it finally exhausts its nuclear fuel in another 5 billion years, it will swell into a red giant, shed its outer layers, and leave behind a white dwarf, a dense ember about the size of Earth, slowly cooling over trillions of years. But more massive stars, those born with at least 8 times the sun's mass, follow a very different path. They burn through their fuel much faster, living only millions of years instead of billions. And when they run out of fuel, they don't fade gently. They explode. The process is both violent and brief. When a massive star exhausts the last of its nuclear fuel, there's nothing left to hold up the core against gravity's inward pull. The core collapses in on itself in less than a second. The outer layers, suddenly losing the support of radiation pressure from below, crash inward at a quarter the speed of light. They hit the rebounding core and explode outward in a supernova, one of the brightest events in the universe, briefly outshining an entire galaxy. What's left behind is the core, compressed to incredible densities. If the original star was massive enough, the core collapses all the way into a black hole. But if the star was between about 8 and 25 solar masses, massive, but not quite massive enough for a black hole, the collapse stops at an intermediate stage. The core becomes a neutron star. A neutron star is matter compressed to the edge of what physics allows. Take the mass of the sun, maybe 1.5 times that much, and squeeze it into a sphere only 20 kilometers across. That's about 12 miles. The size of a city. The density is staggering. A single teaspoon of neutron star material would weigh more than 100 million tons on Earth. At these densities, normal atoms can't exist. Electrons get crushed into protons, forming neutrons, hence the name. The star is essentially a giant atomic nucleus, held up against further collapse not by any force we're familiar with, but by neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same quantum state. But neutron stars aren't simple. Despite their name, they're not made purely of neutrons. There's structure to them. The outer kilometer or so forms a crust, a lattice of atomic nuclei and electrons. Incredibly dense, but still organized into something resembling a crystal structure. Below that, things get stranger. There's likely a region where protons form a superconducting phase, carrying persistent electrical currents that maintain the star's magnetic field. And in the very core, at pressures and densities we can barely imagine, matter may break down into its fundamental constituents. Free quarks, exotic states like Bose-Einstein condensates, or forms of matter we haven't even theorized yet. Now here's where magnetars enter the picture. When a star collapses into a neutron star, something interesting happens to its magnetic field. Stars have magnetic fields, though typically not very strong ones. But when a star collapses, conservation of magnetic flux means the field gets compressed along with everything else. Here's the key principle. If you have the linear dimensions of a magnetic field, you increase its strength by a factor of 4. We're taking a field that might span hundreds of thousands of miles and squeezing it down to less than 20 kilometers. A typical neutron star ends up with a field of around 1,000,000,000,000 Gauss, 10 to the 12th power Gauss, or about 10 to the 8th power Tesla if you prefer SI units. But magnetars don't stop there. Something happens during or shortly after the formation of some neutron stars that amplifies the magnetic field by another factor of 1,000. These are the magnetars, with fields reaching 10 to the 15th power Gauss, a quadrillion Gauss, the strongest magnetic fields we know of anywhere in the universe. For a long time, scientists weren't sure exactly how this happened. What could take an already extreme magnetic field and push it into the realm of the impossible? Recent research has started to provide answers, and they involve some remarkable processes. One promising mechanism was worked out in 2020 by a team of scientists from France and Germany. They created detailed computer simulations of what happens inside a proto-neutron star in the first few seconds after its formation. The newborn neutron star is incredibly hot and spinning incredibly fast, potentially up to 1,000 rotations per second. The combination of rapid rotation and intense convective motion in its interior creates a dynamo effect. Think of how Earth's magnetic field is generated. Our planet's outer core is liquid iron, and its motion driven by convection, and the planet's rotation creates electrical currents. Those currents generate Earth's magnetic field. A similar process happens in the Sunday. This is a dynamo mechanism, and it's a standard way for rotating fluids of electrically conductive material to generate magnetic fields. But in a proto-neutron star, this process is amplified beyond anything we see elsewhere. The material is incredibly dense, incredibly hot, and moving incredibly fast. The simulations showed that under the right conditions, fast rotation, intense convection, temperatures of tens of billions of degrees, the dynamo effect can amplify a pre-existing weak magnetic field up to magnetar strength within seconds of the neutron star's formation. This was a major breakthrough. It meant magnetars didn't need to inherit super strong fields from their progenitor stars. A star with a relatively normal magnetic field could collapse into a rapidly rotating neutron star, and the dynamo process alone could generate a magnetar field. The key requirements are rapid rotation. The star needs to be spinning at nearly the breakup velocity, the speed at which centrifugal force would tear it apart, and the right temperature range to drive convection in the interior. But that's not the only way to make a magnetar. They were studying a binary star system called HD 45166, located about 3,000 light-years away in the constellation Monoceros. This system contains what's called a Wolf-Rayet star, a type of massive star that's already shed most of its outer layers, leaving a hot, dense core exposed. Astronomer Tomer Shenar from the University of Amsterdam had been studying HD 45166 for a while. Something about its characteristics didn't quite fit the standard models. On a hunch, he decided to measure its magnetic field using espadons, a specialized instrument at the Canada-France-Hawaii telescope designed specifically for detecting stellar magnetic fields. What he found was remarkable. The Wolf-Rayet star in HD 45166 has a magnetic field of about 43,000 Gauss. That's extraordinarily strong for a living star, about 100 times stronger than the most magnetic massive stars known. But here's what makes it fascinating for the magnetar story. When this star eventually explodes in a supernova, as it inevitably will, its core will collapse into a neutron star. And when that field gets compressed down from the star's current size to neutron star size, it will be amplified to about 100 trillion Gauss. In other words, HD 45166 is a magnetar progenitor. We're watching a future magnetar before it's born. This star will end its life in a supernova, probably within the next few million years, and when it does, it will create one of these magnetic monsters. How did HD 45166 get such a strong magnetic field in the first place? The answer lies in its past. Astronomers believe this star is what's called a blue straggler, the product of two stars that merge together. When stars merge, the process is incredibly turbulent. Material from both stars mixes violently, creating powerful currents and flows. These turbulent motions can generate intense magnetic fields through dynamo action. This suggests a second pathway to magnetars, stellar mergers. If two massive stars in a binary system spiral together and merge, the resulting star can inherit a powerful magnetic field from the merger process. Later, when that merged star explodes and collapses into a neutron star, the already strong field gets compressed and amplified into magnetar territory. Astronomers estimate that about 10% of massive stars in the Milky Way are the products of stellar mergers. This matches fairly well with the estimated fraction of neutron stars that become magnetars. It's not a perfect correlation. Magnetars might form through multiple pathways, but it suggests that stellar mergers could account for a significant fraction, perhaps even most, of the magnetar population. There's potentially a third formation pathway as well. Some magnetars might form through binary interactions that don't involve a merger. Imagine a neutron star in a close binary orbit with a companion star. The neutron star could pull material away from the companion, accreting it onto its surface. This accretion process could spin the neutron star up to very high rotation rates, and the combination of rapid rotation and the accreted material might amplify the magnetic field. This vampire neutron star scenario, where one star feeds on another, represents yet another possible route to creating these magnetic monsters. It's a reminder that the universe is creative in its methods of producing extremes. What all these formation mechanisms have in common is that they're rare. Whether it's the precise combination of rotation and convection in the proto-neutron star, or the uncommon event of a stellar merger, or the specific conditions of binary interaction, something special needs to happen to create a magnetar. Most supernova collapses produce ordinary neutron stars. Only about 1 in 10, by current estimates, produces a magnetar. And once formed, these objects are remarkable not just for their magnetic fields, but for what those fields do to everything around them. Let's talk about what a magnetar actually is, physically, what it looks like, what it's made of, what happens to matter in its presence. Because these aren't just neutron stars with stronger magnets. The magnetic field is so intense that it fundamentally changes how the object behaves. A magnetar, like any neutron star, is about 20 kilometers in diameter. Let's put that in perspective. That's roughly the size of Manhattan, or about 12 miles across. Now pack into that volume about 1.4 times the mass of the Sunday. The density is almost inconceivable. If you could somehow scoop up a teaspoon of material from a magnetar's surface, that teaspoon would weigh more than 100 million tons on Earth. The gravity at the surface is correspondingly extreme. If you could somehow stand on a magnetar, which you absolutely couldn't for many reasons we'll get to, you'd weigh roughly 100 billion times what you weigh on Earth. NASA has a wonderful way of illustrating this. A marshmallow falling onto the surface of a neutron star would hit with the force of 1,000 hydrogen bombs. But gravity, extreme as it is, isn't even the main story here. The magnetic field is. And that field is so powerful, it does things we simply don't see anywhere else in the universe. Earth's magnetic field, the one that makes compass needles point north and creates the beautiful aurora at our poles measures about half a Gauss, maybe up to 0.6 Gauss in some places. It's enough to guide birds and protect us from solar radiation, but by any cosmic standard, it's incredibly weak. A refrigerator magnet has a field of about 100 Gauss. That's 200 times stronger than Earth's field. The powerful electromagnets used in hospital MRI machines produce fields of a few Tesla, that's tens of thousands of Gauss. These are among the strongest magnetic fields we can reliably produce and control. A typical neutron star has a surface magnetic field of about 1 trillion Gauss. That's 10 to the 12th power Gauss. This is already so far beyond anything in our experience that it's hard to comprehend. At these field strengths, atoms start to behave strangely. The magnetic field is strong enough to affect the motion of electrons around atomic nuclei. But a magnetar has a field of 10 to the 14th to 10 to the 15th power Gauss, 100 trillion to a quadrillion Gauss. That's 1,000 times stronger than an already extreme neutron star, 1 billion times stronger than the strongest field we can create in a laboratory, and 1 trillion times stronger than Earth's field. At this point, we've left the realm of the merely extreme and entered something altogether different. The magnetic field of a magnetar is so powerful that it has an energy density comparable to mass. Remember Einstein's famous equation? E equals mc squared? In a magnetar's field, the energy density is so high that when you divide by c squared to get an equivalent mass density, you get a value that's more than 10,000 times the density of lead. The magnetic field effectively has weight. This field can distort atoms. Normal atoms are more or less spherical, with electrons occupying shells at various distances from the nucleus. But in a magnetar's field, atoms get squeezed. They stretch out into long, thin cylinders, like needles. A hydrogen atom, which is normally round and about an angstrom across, becomes squeezed into a shape that's 200 times narrower in the direction perpendicular to the field lines. These elongated atoms can actually form long chains, linking together into polymer-like structures across the magnetar's surface. The surface chemistry is nothing like anything we know on Earth. Covalent bonds, the normal chemical bonds that hold molecules together, simply don't work the same way. Molecular chemistry, as we understand it, becomes impossible. And this is just what happens to atoms. What about more complex matter? What about, say, a human body? At a distance of about 1,000 kilometers from a magnetar, roughly 600 miles, the magnetic field becomes lethal to any form of life. Not because of radiation, though there's plenty of that, but because the magnetic field itself starts to tear apart your molecular structure. Our bodies rely on chemistry. Nerve signals are chemical and electrical processes. Our cells maintain their structure through chemical bonds. All of this breaks down in the magnetar's field. The field doesn't just disrupt your biochemistry, it distorts the very atoms you're made of. At these distances, you wouldn't just die, you'd dissolve. Your molecular bonds would break, your atoms would stretch and deform. Even from thousands of kilometers away, the field is powerful enough to disrupt electron clouds, the fuzzy probability distributions that describe where electrons exist around atomic nuclei. When those electron clouds get warped, atoms can't bond properly. Chemistry stops working. And we haven't even gotten to some of the really weird effects yet. Remember that thought experiment about the credit cards? At a distance halfway between Earth and the Moon, about 192,000 kilometers, or nearly 120,000 miles, a magnetar's magnetic field is still strong enough to wipe the magnetic strip on every credit card on Earth. The field reaches across that vast distance and erases the organized patterns of magnetization that store your card's data. To put this in perspective, the Moon orbits Earth at an average distance of about 384,000 kilometers. We're saying that a magnetar placed at the halfway point nearly 250,000 kilometers away could still magnetically interact with objects on Earth's surface. That's the kind of reach these fields have. But the magnetar itself is only 20 kilometers across. The field extending from such a tiny object creates incredible gradients, places where the field strength changes dramatically over short distances. These gradients produce forces that can rip things apart on molecular and atomic scales. The structure of the magnetar itself is fascinating and still not fully understood. Like any neutron star, it probably has a layered structure, like a cosmic M and M, as NASA astrophysicist Todd Strohmeyer puts it. At the center is the core, and here things get truly speculative. The pressure and density are so extreme that matter might exist in forms we've never observed. It could be a soup of neutrons and protons. It might contain unconfined quarks, the fundamental particles that normally combine to form neutrons and protons. There could be exotic states of matter like Bose-Einstein condensates, where quantum effects operate on macroscopic scales. We simply don't know for certain. Surrounding the core is an intermediate layer. And this is where something remarkable happens. Scientists believe that at these depths, protons form a superconducting phase, a state where they can carry electrical currents without any resistance. These persistent electrical currents are likely what maintains the magnetar's powerful magnetic field over time. Then comes the crust. This is a layer about 1 kilometer thick, and it's made primarily of atomic nuclei and electrons, arranged in a crystal lattice. Todd Strohmeyer calls it the strongest material that we know of in the universe, and he's right, at least by some measures. The crust has an incredible resistance to stress and deformation. But here's the crucial thing. It's not quite strong enough. The magnetic field threads through this crust, coupling the interior of the star to the solid surface. The magnetic field and the crust are locked together. Changes in one affect the other, and the interior of the magnetar is fluid, constantly in motion. As it moves, the magnetic field gets twisted and wound up like a rubber band being turned over and over. This places enormous stress on the crust. The crust is solid. It can't easily flow or deform to relieve that stress. So the stress builds and builds. The magnetic field exerts forces on the crust measured in incredible values, forces that would instantly vaporize any earthly material. Eventually, despite being the strongest material in the universe, the crust can't take it anymore. It cracks. And when a magnetar's crust cracks, the universe takes notice. Starquakes. The name sounds almost gentle, doesn't it? Like the celestial equivalent of an earthquake, which, while devastating to us, is just the Earth's crust shifting slightly, releasing built-up stress along fault lines. But a starquake on a magnetar is something entirely different. It's one of the most violent events in the universe, short of a supernova or black hole merger. The process begins with the relationship between the magnetar's crust and its magnetic field. Remember that the interior of the magnetar is fluid, a dense, roiling soup of neutrons, protons, and exotic particles. This fluid is in constant motion, driven by convection and the star's rotation. The magnetic field is anchored in this fluid, and as the fluid moves, the field gets twisted and reorganized. But the field also passes through the solid crust on its way to the exterior. It's like trying to twist a rope that's threaded through a rigid pipe. The pipe resists the twisting, and stress builds up at the connection points. Over time, we're talking months or years, this stress accumulates. The magnetic field is trying to reorganize itself into a lower energy configuration, but the solid crust is holding it in place. Electromagnetic forces, measured in incredible magnitudes, pull at the crust from the inside. The crust distorts, bends, stores elastic energy like a spring being compressed. The crust is incredibly strong. That matters. If it were weak, it would just flow or deform continuously, and stress wouldn't build up, but it's rigid. And so the stress keeps mounting until finally, at some critical point, the crust fails. It cracks. The crack itself can be several kilometers long on a star that's only 20 kilometers in diameter. In the European Space Agency's analysis of the 27th of December 2004 event, they estimated the fracture in SGR 1806 to 20 was about 5 kilometers across. That's a quarter of the star's diameter. It would be like a crack forming across the entire North American continent on Earth. When the crust cracks, several things happen almost simultaneously. The magnetic field, suddenly released from the constraint of the solid crust, snaps into a new configuration. This is like releasing a twisted rubber band. The energy stored in the twist is suddenly converted to motion. But instead of a rubber band untwisting, you have a magnetic field that extends across thousands of kilometers, carrying energy densities comparable to mass, suddenly reorganizing itself. The crack itself releases seismic energy. The crust shifts by only about a centimeter, maybe an inch or so. But remember the density of this material. Remember the forces involved. That centimeter of motion in material this dense, under this much stress, releases energy on a scale that's hard to fathom. On an earthquake's Richter scale, this event would register as a magnitude 23. The Richter scale is logarithmic. Each integer represents a tenfold increase in amplitude and roughly 31.6 times more energy. The largest earthquake ever recorded on Earth was the 1960 Valdivia earthquake in Chile, which measured 9.5 on the Richter scale. A magnitude 23 earthquake would be about 10 to the 13.5 power, roughly 30 trillion times more powerful. But we're not done yet. The real violence comes from what happens next. When the magnetic field reorganizes, it accelerates charged particles to incredible energies. Electrons and positrons, matter and antimatter, are created from the intense electromagnetic fields. The field is so strong that it literally creates particle-antiparticle pairs out of the vacuum. These particles immediately begin annihilating each other, producing gamma rays. A fireball forms on the surface of the magnetar. Think of it as a bubble of superheated plasma, alive with gamma rays and charged particles, magnetically confined but intensely hot and energetic. This bubble can extend hundreds or even thousands of kilometers above the star's surface, held in place by the immense magnetic field. A brilliant beam of radiation connects this bubble to the surface like a thread of pure energy. The magnetar continues spinning, and as it does, the bubble rotates with it. From our vantage point, we see this as pulsations in the gamma ray and X-ray emission. Every time the bubble rotates into our view, we see a pulse of radiation. For SGR 1806 to 20, this pulse repeated every 7.56 seconds, matching the star's rotation period. Over the course of minutes, the bubble slowly subsides. It's drawn back down toward the surface along those magnetic field lines, like a ball dropping on New Year's Eve, eventually merging back into the star. But during those few minutes, the magnetar is essentially a spotlight sweeping across the cosmos, beaming out more energy per second than our sun produces in years. This is what happened on the 27th of December 2004, but it's not an isolated event. Magnetars produce smaller bursts all the time, brief flares lasting a fraction of a second, releasing energies equivalent to years of the sun's output. But these giant flares, these massive starquakes, are rare even by magnetar standards. In the past 40+ years of observations, astronomers have only definitively recorded 3 giant flares from magnetars. The first was detected on the 5th of March 1979 from a source in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 160,000 light-years away. At the time, scientists didn't understand what they were seeing. The burst saturated instruments on several spacecraft, including 2 Soviet Venera probes that were in heliocentric orbit after completing their Venus missions. The burst lasted only about 1/5 of a second initially, but during that time, it released more energy than our sun had emitted since the building of the pyramids. Astronomers were stunned. Nothing in their understanding of the universe could explain such a blast of energy from a source that wasn't obviously a supernova or some other known phenomenon. The key breakthrough came later in that initial burst. After the main spike faded, observers detected a pulsating tail, a series of smaller pulses repeating every 8 seconds. This was the signature of rotation. Whatever had exploded was spinning and spinning at a rate consistent with a neutron star. Over time, scientists worked out that this must have been a special type of neutron star with an incredibly strong magnetic field. This event played a crucial role in the development of the magnetar hypothesis. The second giant flare came in 1998, also detected from a soft gamma repeater. These events are so rare that going nearly 2 decades between giant flares seemed normal. Astronomers started to understand the pattern. These were starquakes, catastrophic fractures in the crusts of highly magnetized neutron stars. Then came the 27th of December, 2004. An SGR 1806-20 showed that even among magnetar giant flares, there could be extraordinary outliers. The observations of this event were unprecedented in their detail. Anna Watts, an astrophysicist at the University of Amsterdam, led an analysis using data from NASA's Fermi Gamma Ray Space Telescope. Fermi had observed another magnetar, SGRJ 1550-5418, located about 15,000 light-years away, in the constellation Norma, during a period of intense activity in 2008 and 2009. This magnetar went into what can only be described as a storm. At times, it was producing hundreds of bursts in as little as 20 minutes. These weren't giant flares, they were smaller events, but they happened with such frequency and in such numbers that they provided an unprecedented opportunity to study starquake dynamics. Watts and her team analyzed 263 individual bursts detected by Fermi's gamma-ray burst monitor. What they found was fascinating. Embedded in the gamma-ray signals were vibrations, actual oscillations of the neutron star itself. These vibrations are called quasi-periodic oscillations, or QPOs, and they provide a window into the magnetar's interior. When the crust cracks, it sends shear waves similar to the S waves in an earthquake propagating through the star. These waves bounce back and forth, creating standing wave patterns. The entire star vibrates in complex modes, with the crust and core bound together by the super-strong magnetic field, oscillating in tandem. By analyzing the frequencies of these oscillations, scientists can learn about the magnetar's internal structure, its mass distribution, the stiffness of the crust, the properties of matter at nuclear densities. It's a technique called asteroseismology, and it's similar to how seismologists on Earth use earthquake waves to map our planet's interior. But why do these starquakes happen at all? And more specifically, why do they happen when they do? This question puzzled astronomers for years. Magnetars don't produce bursts on any predictable schedule. Some go quiet for years, then suddenly become active. Some produce many small bursts, but never a giant flare. Others seem to save up their energy for one massive event. What determines this behavior? Rosalba Perna, a fellow at the Astronomical Observatory of Trieste, and her colleague José Pons at the Universitat d'Alacant in Spain, addressed this question through computer simulations. They created detailed models of magnetar magnetic fields and how they evolve over time. What they found was that the geometry of the magnetic field matters just as much as its strength. A magnetar with a highly twisted or complex field configuration experiences more stress in its crust than one with a simpler, more orderly field. The field's topology, how the field lines are arranged, Whether there are knots or tangles in the field determines where stress builds up and how quickly. They also found that magnetar activity changes with age. Young magnetars, freshly formed and still hot, tend to be more active. They produce bursts more frequently and release more energy per burst. As the magnetar ages, cools, and its magnetic field gradually decays, the activity level decreases. Older magnetars are quieter. This explained a mystery. Some magnetars with apparently similar field strengths behave very differently. One might be erupting constantly, while another stays quiet. The difference lies in their ages and the detailed geometry of their magnetic fields, not just the raw field strength. It's also why giant flares are so rare. These massive events require not just a strong magnetic field, but a specific configuration. A lot of stored magnetic energy in a configuration that can be released all at once. Most starquakes are smaller because they're releasing localized stress in limited regions of the crust. But occasionally, conditions align for a global reconfiguration of the magnetic field. In the 3 giant flares observed so far, each has been unique. The 1979 event was powerful, but not as extreme as 2004. The 1998 event fell somewhere in between. SGR 1806-20's December 27th outburst was roughly 100 times more energetic than either previous giant flare. Scientists still don't fully understand why this particular event was so extreme. The leading theory involves a particularly catastrophic reorganization of SGR 1806-20's magnetic field. The magnetar may have been storing magnetic energy for a long time, building up a highly unstable configuration. When the crust finally failed, the resulting magnetic reconnection, the snapping and rejoining of magnetic field lines, released an enormous amount of stored energy all at once. There's also speculation that the interior magnetic field of SGR 1806-20 is even stronger than its surface field suggests. The surface dipole field we can measure might represent only a fraction of the total magnetic energy stored in the star's interior. If true, this would explain how such an incredible amount of energy could be available for release. But we still don't know for sure. We don't know what triggers these giant flares. We don't know if a magnetar that's produced one giant flare can produce another, or if the first flare exhausts the available magnetic energy. We don't know if we should see aftershocks in the days following a giant flare, as we would after an earthquake, though so far, the data hasn't clearly shown them. What we do know is that when a magnetar decides to crack its surface, it becomes one of the most luminous objects in the universe. And on the 27th of December 2004, we got to see this process in action, in more detail than ever before. Let's return to that day, the 27th of December 2004. It was a Sunday. For most people, it was a quiet day between Christmas and New Year's. In much of the world, it was an ordinary late December afternoon or evening. But at 21 hours, 30 minutes, and 26 seconds, Universal Time, that's 4:30 p.m. Eastern Standard Time, something extraordinary happened. The blast was detected almost immediately by spacecraft across the solar system. It wasn't aimed at us. Particularly, magnetar flares radiate roughly equally in all directions, but we happened to be in the line of sight, and the intensity was such that it didn't matter which direction you were looking from. Mars Odyssey, orbiting the red planet, was one of the first to register the event. Its radiation detectors were designed to measure the radiation environment around Mars. Suddenly, they were overwhelmed by a flood of gamma rays and X-rays coming from deep space. NASA's Swift satellite had been launched just 5 weeks earlier, on November 20th, 2004. It was designed specifically to detect and study gamma-ray bursts, the brilliant flashes from dying massive stars in distant galaxies thought to be associated with the formation of black holes. Swift was equipped with sensitive detectors that could trigger automatically when they detected a gamma-ray burst, then rapidly slew the entire spacecraft to point its telescopes at the source. But Swift wasn't pointing anywhere near Sagittarius when SGR 1806-20 erupted. It didn't matter. The blast of gamma rays and X-rays was so intense that it passed straight through the body of the spacecraft and saturated Swift's detectors anyway. It was like trying to measure the brightness of a searchlight with your eyes closed. The light is so bright it comes through your eyelids anyway. RHESI, the Reuven-Ramati High Energy Solar Spectroscopic Imager, was in Earth orbit, studying the Sunday. It was designed to observe solar flares and other energetic solar phenomena in X-rays and gamma rays. RESI's detectors also saturated. The burst from SGR 1806-20, arriving from the opposite side of the sky from the Sun, was bright enough to completely flood an instrument designed to observe solar flares at close range. Integral, the European Space Agency's International Gamma-Ray Astrophysics Laboratory, saw the burst. So did Cassini, all the way out at Saturn. So did Ulysses, in its elongated heliocentric orbit. More than a dozen spacecraft in total detected the event. Some of these spacecraft were sophisticated enough to track the burst in real time and record its evolution. The initial spike lasted only about 0.2 of a second, the time it takes you to blink. But in that fraction of a second, SGR 1806-20 released 1 × 10⁻⁴ joules of energy. To put that in perspective, the Sun's total energy output is about 3.8 × 10⁻26 power watts, which is joules per second. In 1/10 of a second, SGR 1806-20 released as much energy as the Sun produces in somewhere between 150,000 and 250,000 years. Depending on how you do the calculation, different teams arrived at slightly different numbers, but they're all in that ballpark, hundreds of thousands of years of solar output in the time it takes to snap your fingers. The absolute magnitude of the burst in gamma rays was about -29. For comparison, the Sun's absolute magnitude in visible light is about 4.8. The difference of about 34 magnitudes means this burst was, in gamma rays, roughly 100 million times intrinsically brighter than the Sun in visible light. If you could have seen gamma rays with your eyes, SGR 1806-20 would have briefly outshone the full moon, even though it was 50,000 light-years away. After the initial spike, the burst didn't just stop. It continued, though at lower intensity, for 6 more minutes. This tail phase showed clear pulsations, pulses of radiation arriving every 7.56 seconds with remarkable regularity. This was the rotation period of the magnetar being stamped onto the outgoing radiation. The hot spot created by the crack in the crust was rotating in and out of view like a lighthouse beam. But the spacecraft observations, incredible as they were, weren't even the most remarkable part. The blast had measurable effects on Earth itself. Earth's ionosphere is a region of the upper atmosphere, starting at about 80 kilometers altitude and extending upward. In this region, ultraviolet light from the Sun strips electrons from atoms and molecules, creating a layer of ionized gas. The ionosphere is important for radio communications. The ionosphere's properties change between day and night. During the day, solar UV light maintains high ionization levels. At night, ionization decreases as atoms and molecules recombine, capturing free electrons again. When the gamma rays from SGR 1806-20 hit Earth's atmosphere, they ionize the air just like solar UV does, but more suddenly and more intensely. For a brief period, the ionosphere lit up. The side of Earth facing Sagittarius experienced a sudden increase in ionization. In terms of its electrical properties, the nighttime ionosphere briefly resembled the daytime ionosphere. This was detected by multiple ground-based instruments. Radio operators noticed sudden disturbances in low-frequency radio signals. One amateur astronomer, Paul Campbell in Edmonton, Alberta, was monitoring a U.S. Navy radio transmitter in Washington state when the burst hit. He recorded a sharp spike in signal strength at the exact moment of the gamma ray arrival. The enhanced ionosphere was reflecting radio waves more efficiently, but it went beyond the ionosphere. The magnetic field of Earth itself responded to the blast. When the initial burst of radiation hit the magnetosphere, the magnetic bubble that surrounds Earth, it compressed our planet's field. Like a gust of solar wind, but much more sudden, ground-based magnetometers detected a disturbance in Earth's magnetic field. This wasn't a huge shift. We're not talking about compasses suddenly pointing the wrong direction. But it was measurable. The magnetic field rang like a bell struck by a hammer, oscillating slightly before settling back to its normal configuration. And remarkably, there appears to have been a permanent, tiny shift in the field. The Magnetars blast, from 50,000 light-years away, had left a permanent mark on Earth's magnetic field. The European Space Agency's cluster and double-star missions, though designed to study Earth's magnetosphere rather than distant cosmic events, made crucial observations. These satellites happened to be in the right place at the right time, and their instruments weren't saturated by the gamma rays because they weren't designed to detect high-energy radiation. Instead, they measured particle fluxes and magnetic field variations. Professor Steve Schwartz of Imperial College London led the analysis of this data by examining the first 100 milliseconds of the event in exquisite detail. His team identified 3 distinct timescales in the burst's rise. These timescales were crucial clues to what had happened on the magnetar's surface. Based on models of crustal mechanics and magnetic field dynamics, Schwartz and his colleagues concluded that they were seeing direct evidence of the crust fracturing. The different timescales corresponded to different phases of the crack propagating through the crust and the magnetic field responding. They were even able to estimate the size of the fracture, about 5 kilometers across. Think about that for a moment. A crack formed in the surface of a dead star 50,000 light-years away halfway across the galaxy. And by analyzing the pattern of gamma rays that reached Earth, scientists could determine the size of that crack. It's an extraordinary feat of detective work. In the Arctic, fishermen reportedly saw auroras appear suddenly in the sky at the moment the burst arrived. Auroras are caused by charged particles from the sun interacting with Earth's magnetic field and upper atmosphere. The particles spiral along field lines toward the poles, where they collide with atmospheric atoms, causing them to glow. The burst from SGR 1806 to 20, carrying immense electromagnetic energy, triggered aurora-like phenomena even in people's local nighttime skies. All of this from 50,000 light-years away. The light travel distance is worth emphasizing. When the starquake happened on SGR 1806 to 20, the radiation began racing outward at the speed of light. It traveled across the galaxy for 50,000 years. When it finally reached Earth on the 27th of December 2004, humans had existed in our modern form for only about 200,000 years. The radiation began its journey before our species had spread across Earth, before we developed agriculture or built cities. It crossed the void of space while we lived in caves, then in villages, then in civilizations. It arrived finally in an age when we had spacecraft in orbit capable of detecting and analyzing it. Or to put it another way, the starquake that cracked SGR 1806 to 20's crust happened about 50,000 years ago. The radiation took that long to cross the galaxy and reach us. That means this occurred around 48,000 BCE. Neanderthals still walked the earth. Homo sapiens were just beginning to create sophisticated art and tools. And on the far side of the galaxy, a dead star's crust cracked, sending radiation racing across space toward a planet where, millennia in the future, beings capable of understanding what they were seeing would observe its arrival. If SGR 1806 to 20 had been closer, the consequences could have been dire. Scientists calculated that if this same blast had occurred within about 10 light-years of Earth, it would have been catastrophic. The gamma radiation would have struck our atmosphere with enough intensity to trigger chemical reactions that destroy ozone. Our ozone layer, which protects us from the sun's ultraviolet radiation, would have been severely damaged or destroyed entirely. The effects would have been similar to a major nuclear exchange, though from an entirely natural cause. Within 6 light-years, the damage would have been even worse. The radiation would have been intense enough to severely harm any organism on Earth's surface. It could potentially have triggered a mass extinction event. But we're lucky. The closest known magnetar is AXP 1E1048 to 59, about 9,000 light-years away. Even if it produced a giant flare similar to SGR 1806 to 20's, we'd be far enough away that the effects would be interesting scientifically but not dangerous to life. Still, the December 27th event raised intriguing questions. The most famous is the one that ended the age of dinosaurs 66 million years ago, now known to have been caused by an asteroid impact. The Ordovician extinction, the Devonian extinction, the Permian-Triassic event that wiped out 96% of marine species, each has been attributed to various causes, like volcanism, climate change, or asteroid impacts. Could any of these have been caused, or at least contributed to, by a magnetar flare? Probably not. Most scientists think the magnetar would need to be incredibly close, and while stars do move relative to each other over millions of years, the chances of a magnetar passing within 10 light-years of Earth seem very low. But it's a reminder that we live in a universe full of potential dangers, most of which we're fortunately shielded from by the sheer vastness of space. The 27th of December 2004 event remains the most powerful stellar explosion ever witnessed from our galaxy. It's been surpassed in apparent brightness only by a few gamma-ray bursts from other galaxies billions of light-years away. But those involve different physics, likely the formation of black holes from collapsing supergiant stars. As far as magnetar flares go, SGR 1806 to 20's outburst remains the king. And yet, as extreme as this event was, it represents just one aspect of magnetar physics. The magnetic fields of these objects do something even stranger than crack their crusts and unleash gamma-ray hell. They do something that physics predicts, but that we've only recently begun to observe directly. They change the nature of empty space itself. There's a concept in physics that sounds more like philosophy than science. The vacuum isn't empty. This idea goes back to quantum mechanics, and specifically to quantum electrodynamics, the theory developed in the 1920 seconds and 1930 seconds that describes how light and matter interact at the quantum level. In the quantum world, the vacuum, what we think of as empty space, is actually seething with activity. Virtual particles constantly pop into existence in matter-antimatter pairs, exist for the briefest instant, then annihilate each other. These aren't real particles in the sense that they can be detected or interact with things around them under normal circumstances. They're called virtual because they exist only in the gaps allowed by the Heisenberg uncertainty principle, borrowing energy from the vacuum for such a short time that they can't be directly observed. This sounds strange, but the effects of these virtual particles are real and measurable. they cause tiny shifts in the energy levels of electrons in atoms. They create a force between metal plates placed close together in a vacuum, the Casimir effect. It's a quantum foam of virtual particle-antiparticle pairs, constantly appearing and vanishing. In 1934, physicists Werner Heisenberg and Hans Euler worked out what should happen to this quantum vacuum in the presence of a very strong magnetic field. In a classical picture, the physics you learn in high school, a magnetic field in vacuum doesn't affect light. Light just passes through, unimpeded. Empty space is transparent to electromagnetic radiation, regardless of any magnetic fields present. But in quantum electrodynamics, this isn't quite true. Heisenberg and Euler showed that if a magnetic field is strong enough, it can affect the behavior of those virtual electron-positron pairs. The magnetic field can polarize the vacuum, causing the virtual pairs to align with the field. And once they're aligned, they affect how real photons, real light, travels through the space. The vacuum, in the presence of a sufficiently strong magnetic field, becomes birefringent. Birefringence is a property you see in certain crystals like calcite. If you pass light through a birefringent crystal, the light behaves differently depending on its polarization, the direction in which its electric field oscillates. Light polarized parallel to the crystal's axis travels at a different speed than light polarized perpendicular to the axis. This can cause a single ray of light to split into two rays, or it can cause the polarization direction to rotate. Heisenberg and Euler predicted that empty space in a strong enough magnetic field would act like a birefringent crystal. Light with its polarization parallel to the magnetic field would travel at a different speed than light with perpendicular polarization. Both speeds could be slightly less than the normal speed of light in vacuum. But how strong does the magnetic field need to be for this effect to occur? Heisenberg and Euler calculated a critical field strength, 4.41 times 10 to the 13th power Gauss, or about 4.4 billion Tesla. This is called the Schwinger limit, or the QED, critical field. This is an incredibly strong field, far stronger than anything we can create on Earth. The most powerful, sustained magnetic fields we can generate in laboratories are measured in hundreds of Tesla. Pulsed magnets, which create brief bursts of field, can reach thousands of Tesla before they destroy themselves. The QED critical field is 1,000,000 times stronger than anything we can create. But magnetars exceed this critical field. Their surface fields are 10 to the 14th to 10 to the 15th Gauss, 10 to 100 times stronger than the QED critical field. The vacuum around a magnetar should definitely be birefringent. For decades, this was a prediction without direct confirmation. Vacuum birefringence had never been observed. The PV-LAS experiment in Italy, Polarizzazione del vuoto con laser, spent years trying to detect the effect using lasers and powerful electromagnets. Despite their best efforts, the magnetic fields they could generate weren't strong enough to produce a measurable effect. But magnetars offer a natural laboratory. If we could measure the polarization of light coming from a magnetar in enough detail, we might be able to detect the signature of vacuum birefringence. The challenge is that polarization can be affected by many things: the magnetar's atmosphere, its surface magnetic field structure, the geometry of how we're viewing it. All of these can polarize light. To prove you're seeing vacuum birefringence, you need to show that the observed polarization can't be explained by these other effects alone. In 2017, a team led by Roberto Turolla studied the optical light from a neutron star called RxJ 1856, 5 to 3754. They detected linear polarization in the visible light coming from this object, which has a magnetic field around 10 to the 13th Gauss, just at the threshold where vacuum birefringence effects might be detectable. The polarization they observed was intriguing, but it wasn't definitive proof. The statistical significance wasn't quite strong enough, and there were other potential explanations for the polarization. It was a hint, but not confirmation. The breakthrough came in 2025. A team led by Rachel Stewart from George Washington University, working with colleagues from Rice University, NASA Goddard, and several other institutions, observed a magnetar called 1E1547, 0 to 5408, using multiple space-based telescopes. The key instrument was the Imaging X-ray Polarimetry Explorer, or IXPE, a NASA mission launched specifically to measure X-ray polarization from cosmic sources. They combined IXPE's observations with data from NICER, the Neutron Star Interior Composition Explorer, mounted on the International Space Station, and radio observations from the Parkes Telescope in Australia. What they found was remarkable. The X-ray emission from 1E, 1547 to 5408, showed a very high degree of polarization. At an energy of 2 keV, that's 2000 electron volts, in the soft X-ray range, the phase average polarization was 65%. At certain phases in the magnetar's rotation, the polarization rose to nearly 80%. For context, that's an extraordinarily high polarization. But the really telling feature was how the polarization changed with energy. From 2 keV to 4 keV, there was a strong drop in the polarization degree. This energy-dependent behavior is exactly what's predicted by models that include vacuum birefringence. Here's why. X-rays coming from the magnetar's surface have to pass through a thin atmosphere of hot plasma above the surface. In this plasma, photons can convert between different polarization modes, a process called mode conversion. This mode conversion is most efficient at a specific energy called the QED vacuum resonance, which depends on the plasma density and magnetic field strength. Around this resonance energy, photons can switch polarization modes easily, which reduces the net polarization we observe. Away from this resonance energy at lower energies, where they observe the high polarization, or at higher energies the mode conversion is less efficient, and vacuum birefringence dominates. The vacuum birefringence causes the polarization modes to propagate independently, maintaining high polarization. But right around the resonance, the modes mix, and polarization is reduced. The team created detailed models of the magnetar's atmosphere and magnetosphere, including vacuum birefringence effects. They found that the observed polarization behavior, both the high polarization at 2 keV and the decrease at higher energies, could not be explained without including vacuum birefringence. They also used constraints from radio observations. The radio emission from magnetars comes from their magnetospheres and has its own polarization properties. By combining the X-ray and radio polarization measurements, they could constrain the geometry of the magnetar's magnetic field and viewing angle. This further confirmed that vacuum birefringence was necessary to explain all the observations together. This is strong evidence, probably the best evidence to date, that we're seeing vacuum birefringence occurring naturally in the extreme magnetic fields of a magnetar. It's a prediction of quantum electrodynamics being confirmed in a regime we could never reach in a laboratory. What does this mean? It means that the magnetic field of a magnetar is so strong, it's changing the properties of space-time itself. The vacuum, the empty space between particles, isn't behaving like normal empty space anymore. It has become, effectively, a material medium with optical properties. It's as if the region around a magnetar is filled with an invisible crystal that bends and polarizes light. At these field strengths, other exotic effects occur too. X-ray photons can split into 2 lower energy photons, or 2 photons can merge into 1 higher energy photon. The vacuum can spontaneously create electron-positron pairs if the field gets intense enough, and in the very strongest magnetar fields, right at the surface, this probably happens. Virtual particles become real. The quantum foam of the vacuum gets stirred into a frenzy. The normally ephemeral virtual particles that pop in and out of existence on timescales too short to measure start existing long enough to interact with real photons and with each other. Atoms, as we mentioned before, get stretched into needles. But it's more than just the atoms themselves. The fundamental quantum mechanics that governs how electrons behave around nuclei changes. The allowed energy levels shift. The wavelengths of light that atoms can absorb or emit change. Chemistry, as we understand it, breaks down because the underlying quantum mechanics has been altered by the magnetic field. This is physics at the very edge of what we understand. The theories that predict these effects, quantum electrodynamics, combined with general relativity for the strongest gravity, have been tested extensively in laboratories and in various astrophysical contexts. They're among the most precisely verified theories in all of science. But magnetars push these theories into regimes where they've never been tested before. There are even more extreme theories that predict stronger effects. One is called Born-Infeld electrodynamics, an alternative to standard QED that was originally proposed to solve certain theoretical problems. In Born-Infeld theory, the nonlinear effects in strong fields are even more pronounced than in standard QED. Magnetars might allow us to test whether Born-Infeld theory is correct or whether standard QED continues to hold even at these extremes. Future X-ray polarimetry missions, with even better sensitivity than IXPE, could measure vacuum birefringence effects in detail. They could test QED to unprecedented precision. They could potentially detect deviations that hint at new physics beyond the standard model. But vacuum birefringence is just one aspect of the strange environment around magnetars. These effects are occurring in objects that, despite their incredible power, don't last very long at all. 10,000 years. That's roughly how long a magnetar remains active. 10,000 years of producing X-ray emission, gamma-ray bursts, starquakes, and all the extreme phenomena we've been discussing. Then the magnetic field decays, the activity ceases, and the magnetar becomes just another neutron star, still dense, still bizarre, but no longer one of the universe's monsters. To put that lifespan in perspective, 10,000 years ago, humans were just beginning to transition from hunter-gatherer societies to agriculture. The oldest cities in the world hadn't been built yet. Writing hadn't been invented. From a human standpoint, 10,000 years is a vast span of time, covering most of recorded and much of prehistoric human history. But cosmically, it's nothing. The sun will shine for about 10 billion years total. Typical neutron stars can emit as radio pulsars for millions or billions of years. White dwarfs cool over trillions of years. Even ordinary main-sequence stars, much more massive than the sun, last for millions of years. A magnetar's active lifetime is, by comparison, a brief flicker. Why so short? The answer has to do with where the magnetar's energy comes from. Normal stars are powered by nuclear fusion in their cores. They shine because they're converting hydrogen into helium, releasing energy in the process. This energy supply can last billions of years for a star like the sun, or millions of years for a much more massive star. Neutron stars, being dead stellar cores, don't have nuclear fusion. Radio pulsars, ordinary neutron stars that emit beams of radio waves, are powered by their rotation. They're spinning very rapidly, and as they spin, they emit electromagnetic radiation. This gradually slows them down, converting their rotational energy into radiation. They can do this for millions or billions of years before spinning down to the point where they're no longer observable as pulsars. But magnetars are different. The magnetic field contains an enormous amount of energy. Remember that energy density we talked about, magnetic energy so concentrated it's comparable to mass. All of that energy is slowly being released. The magnetic field gradually weakens over time, and as it does, the energy goes into heating the star's surface, into producing X-rays and gamma rays, and into driving the starquakes and flares. This decay process happens through several mechanisms. One is ohmic decay, electrical resistance in the crust, causing currents to dissipate. Even though part of the magnetar is superconducting, the currents still flow through regions that have some resistance. And over time, this resistance causes the field to decay. Another mechanism is Hall drift. In the presence of a strong magnetic field and a flow of charged particles, there's a phenomenon called the Hall effect, where the particles drift perpendicular to both the field and their initial motion. In a magnetar's crust, Hall drift can cause the magnetic field to evolve and reorganize. This doesn't directly reduce the total magnetic energy, but it can convert magnetic energy into heat and kinetic energy. There's also the possibility that instabilities in the magnetic field cause it to evolve into configurations with lower total energy. Magnetic field lines can reconnect, annihilating each other and converting magnetic energy into kinetic energy of particles and heat. All of these processes cause the magnetic field strength to decrease over time. And as the field weakens, the magnetar's ability to produce powerful bursts and flares decreases too. Younger magnetars are more active. They produce more bursts, and when they do produce giant flares, those flares tend to be more energetic. The work by Rosalba Perna and Jose Pons showed this clearly in their simulations. A magnetar freshly formed from a supernova with its maximum magnetic field strength is at its most dangerous. As the magnetar ages, its activity level declines. The magnetic field weakens. The stress in the crust builds up more slowly. The X-ray emission, the steady glow that lets us detect magnetars even when they're not bursting, gradually decreases. After about 10,000 years, the magnetic field has decayed to the point where the magnetar is no longer distinguishable from an ordinary neutron star. It may still have a stronger field than typical neutron stars, but not by the orders of magnitude that define a true magnetar. The starquakes cease. The gamma-ray bursts stop. The object goes quiet. This is why magnetars are rare in the observable universe, despite the fact that about 1 in 10 neutron stars is probably born as a magnetar. At any given time, most magnetars have already gone quiet. We only see the currently active ones, and those represent a small fraction of all the magnetars that have ever existed. Scientists estimate there may be 30 million inactive magnetars in the Milky Way galaxy. These are former magnetars that went through their violent phase and are now just ordinary neutron stars, indistinguishable from neutron stars that were never magnetars at all. Meanwhile, we've confirmed only 24 active magnetars. The ratio is staggering for every magnetar we can see. There might be 1 million that have gone dark. Estimating the age of a magnetar is challenging. The traditional method is to measure how fast the magnetar's rotation is slowing down its spin-down rate. As a magnetar emits radiation and ejects particles, it loses angular momentum and spins more slowly over time. By measuring how much it's slowing down, you can estimate how long it's been spinning down and thus how old it is. But this method has problems. It assumes that the magnetic field strength has been constant, which we know isn't true. The field is decaying. It also assumes that the current spin-down rate is representative of the average over the magnetar's lifetime, which might not be true if the magnetar's activity level has changed. Some magnetars seem to violate the expected relationships between field strength, spin-down rate, and age. The most famous example is SGR 0418 plus 5,729. Based on its observed spin-down rate, this magnetar appeared to have a surface magnetic field of only 6 times 10 to the 12th power Gauss. That's about 100 times weaker than a typical magnetar. This was puzzling. Was SGR 0418 plus 5,729 really a magnetar at all, or was it some other type of object? However, more detailed analysis suggested that the surface field measurement wasn't telling the whole story. The internal magnetic field, buried below the crust, could be much stronger. If the field has a strong toroidal component field lines that wrap around the star rather than extending out into space, that component wouldn't be directly measurable from the outside, but it would still contribute to the star's dynamics. Using more sophisticated models that account for magnetic field evolution and the interaction between the internal field and the observable surface field, researchers estimated that SGR 0418 plus 5,729 actually has an internal field strength of about 1 times 10 to the 14th power Gauss solidly in magnetar territory. Different research groups, using various approaches, have estimated its age at anywhere from tens of thousands to several 100,000 years, a wide range that reflects the uncertainties in modeling magnetic field decay. What's clear is that it's older than most known magnetars, which is why its surface field has decayed to lower values. This raises an interesting point. There might be other magnetars out there whose surface fields have decayed to the point where they're not obviously magnetars anymore, but which still have strong internal fields. They might only reveal themselves when they produce a rare burst or flare. This could mean the true magnetar population is larger than we think, and we're only seeing the most active tip of the iceberg. What happens to a magnetar after its field decays completely? It becomes an ordinary neutron star. Depending on its rotation rate and remaining magnetic field, it might continue emitting as a radio pulsar for millions of years. Or it might be too slowly rotating or have the wrong field geometry to produce radio emission, in which case it just becomes a silent, cooling neutron star. Eventually, and we're talking timescales of billions or trillions of years now, it doesn't disappear or decay in any meaningful way. Neutron stars are stable objects. They just cool and fade. Compare this to the fate of other stellar remnants. White dwarfs also cool over trillions of years, eventually becoming black dwarfs, though the universe isn't old enough yet for any black dwarfs to have formed. Black holes, by contrast, can persist essentially forever. The only process that causes a black hole to lose mass is Hawking radiation. And for stellar mass black holes, this process is so slow that it would take 10 to the 60th power years or more for the black hole to evaporate. That's a 1 followed by 60 zeros vastly longer than the current age of the universe. So, magnetars, despite their awesome power, are cosmically ephemeral. They're bright candles that burn intensely for a short time and then go out. We're fortunate that some are currently in their active phases, close enough for us to observe, and happening to flare while we have the technology to detect and study them. But in their brief, active lives, they have profound implications for our understanding of the universe. Magnetars aren't just curiosities, objects to study for their own sake, though they're certainly fascinating enough on their own merits. They're connected to several of the most energetic and mysterious phenomena astronomers are currently investigating. One of the biggest recent connections involves fast radio bursts, or FRBs. These are brief flashes of radio waves from deep space, typically lasting just a few milliseconds. They release as much energy in that brief time as the sun produces in days. Theories range from the mundane to the exotic, from colliding neutron stars to evaporating black holes to, inevitably, alien civilizations. The challenge with FRBs was that most of them didn't repeat, and they came from cosmological distances billions of light years away, which made it impossible to study their source objects in detail. We could see the burst, but not what produced it. Then, in April 2020, something remarkable happened. Astronomers detected an FRB coming from within our own galaxy. The source was SGR 1935 plus 2154, a known magnetar, about 30,000 light-years away in the constellation Vulpecula. This was a game-changer. For the first time, astronomers could definitively link an FRB to a specific type of object, a magnetar. The burst was detected by multiple radio telescopes, including the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, and the STARE-2 array. At the same time, the magnetar also produced X-ray bursts, observed by several X-ray satellites. The energy of this particular FRB was lower than the typical extragalactic FRBs. If it had occurred at cosmological distances, it would have been too faint for most surveys to detect, but it proved the principle. This doesn't mean all FRBs come from magnetars. The universe is large and diverse, and there might be multiple ways to produce these radio flashes. But it does mean that magnetars are likely responsible for at least some FRBs, particularly the ones coming from galaxies relatively nearby. The mechanism is still being actively investigated. One leading theory, though not yet definitively proven, involves starquakes that launch magnetic waves into the magnetar's magnetosphere. These waves can accelerate particles to high energies, and when those particles emit radiation, they produce the coherent radio emission we detect as an FRB. It's similar to the process that produces gamma-ray bursts during magnetar flares, but tuned to radio wavelengths instead. Another major connection involves gamma-ray bursts. We mentioned earlier that SGR 1806-20's giant flare was the brightest event from our galaxy in modern recorded history. But what if it had occurred in another galaxy, tens of millions of light years away? At that distance, we wouldn't be able to see the pulsating tail phase or determine that the source was a neutron star. We'd just see a brief, intense burst of gamma rays, lasting a few tenths of a second. It would look very similar to a class of events called short gamma ray bursts. Short GRBs typically last less than 2 seconds and are thought to arise from the merger of two neutron stars, or a neutron star and a black hole. The merger creates either a larger black hole or, temporarily, an extremely massive neutron star. The process releases enormous energy in the form of a gamma-ray burst. But some short GRBs have properties that don't quite match the merger model. They're a bit softer, lower in energy, or have slightly different durations or afterglow properties. Could some of these actually be giant flares from magnetars in other galaxies? Scientists have calculated that if a magnetar flare like SGR 1806-20's occurred in a galaxy within about 40 megaparsecs, roughly 130 million light-years, it would look like a short GRB. We wouldn't be able to distinguish it from a neutron star merger based on the gamma-ray burst alone. This means that there's potentially an entire subclass of short GRBs that are actually magnetar giant flares. It also means we need to be careful when interpreting GRB observations. Not every short GRB represents the formation of a black hole from merging neutron stars. Some might be just the crust of a magnetar cracking open. There's also a connection to superluminous supernova explosions that are about 100 times more luminous than ordinary supernovae. These are so bright that for a few weeks, they can outshine their entire host galaxies. What powers these extreme explosions? One leading proposed theory is the millisecond magnetar model. In this scenario, when a massive star collapses, it forms a neutron star spinning extremely fast, hundreds or even 1,000 times per second. If this rapidly spinning neutron star also has a magnetar strength magnetic field, it can pump enormous amounts of rotational energy into the surrounding supernova ejecta. The magnetar acts like a central engine, spinning down over days or weeks and converting its rotational energy into electromagnetic radiation and kinetic energy of particles. This extra energy input makes the supernova much brighter and longer lasting than it would otherwise be. Observations support this model. Many superluminous supernovae show light curves their brightness over time that match what you'd expect from a millisecond magnetar powering the explosion. The plateau in brightness that occurs a few hundred seconds to days after the initial explosion, followed by a long, slow decay over years, matches the predicted spin-down of a rapidly rotating magnetar. Similarly, hypernovae, supernovae with exceptionally high kinetic energy, sometimes associated with gamma-ray bursts, might be powered by magnetars. The magnetar provides the extra energy that makes these explosions so extreme. So magnetars aren't just interesting dead stars. They might be central players in some of the most energetic events in the universe. FRBs, certain types of GRBs, superluminous supernovae, and hypernovae. They're engines of cosmic violence, capable of affecting their surroundings even across millions of light years. There's also a more speculative connection: gravitational waves. Einstein's general relativity predicts that massive objects that aren't perfectly spherically symmetric and are accelerating will emit gravitational waves, ripples in space-time itself. Since 2015, the LIGO and Virgo detectors have been observing gravitational waves from merging black holes and neutron stars. A starquake on a magnetar should, in theory, produce gravitational waves. The sudden cracking of the crust, the rearrangement of mass, the oscillations of the star afterward, all of this involves accelerations of large amounts of mass and should create ripples in space-time. The challenge is that the gravitational wave signal from a magnetar starquake would be much weaker than the signal from merging compact objects. LIGO and Virgo might not be sensitive enough to detect such a signal, especially from magnetars tens of thousands of light years away. But next-generation detectors, or a particularly nearby magnetar producing a giant flare, might make detection possible. If we could detect gravitational waves from a magnetar starquake, it would give us an entirely new window into these objects. The gravitational waves would carry information about the star's internal structure, the mass distribution, the stiffness of the crust, the moment of inertia, combined with electromagnetic observations of the same event. This would provide unprecedented constraints on the physics of matter at nuclear densities. Magnetars also serve as natural laboratories for testing fundamental physics. We've talked about vacuum birefringence as a test of quantum electrodynamics, but there are other theories that make predictions in the strong field regime. For instance, some theories of quantum gravity attempts to unify general relativity, and quantum mechanics predict deviations from standard physics at very high energies or in very strong gravitational fields. Magnetars, with their extreme gravitational and magnetic fields, might be places where we could detect these deviations. Any discrepancy between observations and the predictions of standard QED plus general relativity could hint at new physics. Similarly, exotic forms of matter have been proposed to exist in neutron star cores. Quark matter, strange matter, hyperons, Bose-Einstein condensates, all of these could potentially exist at the extreme densities found in neutron stars. Different forms of matter have different properties, which affect the star's radius, mass, moment of inertia, and oscillation frequencies. By observing magnetars in detail, we can constrain what's actually inside these objects. There's even a speculative connection to mass extinctions on Earth. Could a magnetar flare from a nearby source have caused one of Earth's mass extinction events hundreds of millions of years ago? It's an intriguing idea, but probably not likely. The magnetar would need to be within about 6 to 10 light years of Earth, and it would need to produce a giant flare while it was that close. The probability of this happening during Earth's history is very low. Stars move relative to each other, but a magnetar passing that close to Earth during the past few billion years is statistically unlikely. Still, it's a reminder that we live in a universe where such events are possible. Extreme cosmic phenomena can, under the right circumstances. We're fortunate that we live in a relatively quiet corner of the galaxy, far from any currently active magnetars. But for all we've learned about magnetars over the past few decades, profound mysteries remain. Science thrives on questions. Every answer opens new avenues of investigation. Every solved mystery reveals deeper puzzles. Magnetars are no exception. Despite decades of observations and theoretical work, there's still much we don't understand. One of the most basic questions is, why do only about 1 in 10 neutron stars become magnetars? What determines whether a collapsing massive star produces a neutron star with a normal magnetic field or one with a field 1,000 times stronger? We have theories, as we've discussed: rapid rotation in the proto-neutron star, activating a dynamo mechanism; stellar mergers, creating enhanced magnetic fields; binary interactions, spinning up neutron stars and amplifying their fields. But are these the only pathways? Are there multiple routes to making a magnetar, or is there one dominant mechanism we haven't identified yet? And what about the progenitor stars themselves? Is there something special about the stars that produce magnetars? Do they need to have unusually high rotation rates before they collapse? Do they need to be at the high end of the mass range for core collapse supernovae? Or is there an element of chance, the right combination of rotation, convection, and magnetic field at just the right moment during collapse? The discovery of HD 45166 as a magnetar progenitor is a start. But it's just one object. We need to find more magnetar progenitors, study them, and understand what makes them different from stars that will produce ordinary neutron stars. Another mystery involves the giant flares themselves. We've only observed 3 in over 40 years. That's a tiny sample size. We don't know how often these events occur. We don't know if a magnetar that's produced one giant flare can produce another. We don't know if there's a maximum energy for giant flares, or if SGR 1806-20's 2004 event was an outlier that we're unlikely to see again for centuries. If a giant flare releases a significant fraction of the magnetar's stored magnetic energy, can the magnetar build up enough energy for a second flare? Or is the first flare a once-in-a-lifetime event for each magnetar? Answering this question might require waiting decades or centuries for the next giant flare from a known magnetar. There's also the question of aftershocks. On Earth, large earthquakes are typically followed by aftershocks, smaller quakes, as the crust continues to settle into its new configuration. Should we see aftershocks after magnetar starquakes? Some observations hint at this. After a giant flare, or during a period of intense burst activity, magnetars sometimes show complex patterns of smaller bursts in the days or weeks that follow. But it's not clear if these are true aftershocks in the seismological sense, or if they're separate events triggered by the ongoing evolution of the magnetic field. Understanding magnetar seismology in detail could tell us a lot about the interior structure of these objects. Different oscillation modes correspond to waves propagating through different parts of the star. By identifying and characterizing these modes, we could map out the magnetar's interior in a way that's currently impossible with any other technique. The interior structure of neutron stars, magnetars included, remains one of the big open questions in astrophysics. What's the equation of state of matter at nuclear densities? At the center of a neutron star, where the pressure is highest, does matter remain in the form of neutrons, or does it break down into quarks? There's a theoretical possibility called a quark star, where the entire interior is made of free quarks rather than neutrons. There's also the concept of strange matter, a hypothetical form of quark matter containing strange quarks as well as up and down quarks, which might be more stable than ordinary matter. If strange matter exists, it could form strange stars, and some neutron stars we observe might actually be strange stars in disguise. Observations of neutron star masses, radii, and oscillation frequencies can constrain the equation of state. The NICER mission on the International Space Station has been measuring neutron star radii by analyzing the X-ray emission from hotspots on spinning neutron stars. These measurements are starting to narrow down the possible equations of state. But there's still a wide range of possibilities. Does the core contain only neutrons and protons? Hyperons, particles containing strange quarks? Is there a phase transition to quark matter at some density? Is the core a superfluid, a superconductor, or both? Each of these possibilities affects the star's properties: the speed of sound in the interior, the way the star responds to deformations, the oscillation frequencies, the cooling rate. By studying magnetars in detail, especially by observing their oscillations during starquakes, we can start to answer these questions. There's also the mystery of magnetic field stability. Why doesn't a magnetar's magnetic field just collapse or decay rapidly? The field is so intense that naively, you'd expect it to be unstable. In a fluid with no solid support, a purely poloidal magnetic field, one with field lines running from pole to pole, is unstable. The field lines would reconfigure into a lower energy state, releasing magnetic energy. But if there's also a toroidal component field lines that wrap around the star, this can stabilize the field. The toroidal and poloidal components support each other. Computer simulations show that magnetic fields in neutron stars can evolve into stable configurations with a combination of poloidal and toroidal components. But we can't observe the internal toroidal field directly, we can only see the external field. So, we don't know for sure what the ratio of poloidal to toroidal field is, or exactly how the field is structured internally. Understanding this is important not just for magnetars, but for neutron stars in general. Magnetic fields play a role in many neutron star phenomena, from powering pulsar radio emission to affecting the star's spin evolution. Getting the magnetic field structure right is crucial for building accurate models. Another question: are magnetars really as rare as they seem, or are we just missing a lot of them? The known magnetars are all relatively close, within about 50,000 light-years. Most are in our galaxy or nearby dwarf galaxies. But the Milky Way is large, and there might be magnetars hidden behind dust clouds or simply too far away for us to detect their bursts. Most magnetars have been discovered because they produced bursts that were detected by X-ray or gamma-ray satellites. But if a magnetar is going through a quiet phase, or if its bursts happen to be pointed away from us, we might miss it. There could be a population of magnetars we haven't found yet simply because they haven't flared while we were looking. Future X-ray surveys might find quiescent magnetars that aren't currently bursting but are still emitting steady X-rays from their hot surfaces. As our observational capabilities improve, we might discover that magnetars are more common than current estimates suggest. The connection between magnetars and fast radio bursts also raises questions. We know SGR 1935 plus 2154 produced an FRB. But how often do magnetars produce FRBs? Is every magnetar capable of producing radio bursts, or do you need special conditions? And can magnetars explain all FRBs, or just some of them? Some FRBs come from cosmological distances billions of light-years away. For a magnetar burst to be detectable at those distances, it would need to be extremely energetic. It's not clear if magnetar flares can reach those energy levels, or if there's something else going on. There's also a subset of FRBs that repeat producing multiple bursts over time, sometimes from the same location. SGR 1935 plus 2154's FRB didn't show obvious repeats, though the magnetar did produce multiple X-ray bursts. Is FRB repeating related to magnetar burst activity? Or are repeating FRBs a different phenomenon entirely? These are questions that the next generation of radio telescopes, combined with X-ray observations, will hopefully answer. We're entering an era where we can monitor many magnetars continuously and catch them in the act of producing radio emission. Perhaps the deepest question is what magnetars tell us about the nature of matter, fields, and space-time under extreme conditions. These objects exist at the intersection of quantum mechanics, general relativity, nuclear physics, and plasma physics. The vacuum birefringence we discussed, that's quantum field theory, in a regime we can't reach in laboratories. The starquakes, that's the mechanics of matter at densities we can barely imagine. The magnetic field structure, that's magnetohydrodynamics in an environment unlike anywhere else. The gravitational field strong enough that you'd need to include general relativistic corrections to get accurate predictions. All of these pieces interact with each other, The magnetic field affects the structure of the crust, which affects how starquakes propagate, which affects the gravitational wave emission, which is itself modified by the intense magnetic field. You can't study one aspect in isolation. That's part of what makes magnetars so fascinating to physicists. They're natural experiments in extreme physics. Every observation teaches us something about how nature works when you push it to its limits. And we're just beginning. The next few decades will bring new instruments, new observations, new discoveries. We'll find more magnetars. We'll catch more giant flares, hopefully nearby ones that we can study in detail. We'll measure X-ray polarization from more objects, testing vacuum birefringence and probing magnetic field structures. We'll potentially detect gravitational waves from a starquake. Each new piece of data will refine our understanding, answer some questions, and inevitably raise new ones. That's how science works. That's how we gradually build up a picture of the universe, one observation and one insight at a time. Magnetars are part of that grand endeavor. They're reminders that the universe is far stranger and more extreme than everyday experience would suggest. They're laboratories where the laws of physics are tested at their breaking points. And they're objects of beauty in their own way, beautiful in their complexity, in the elegant mathematics that describes them, in the profound questions they raise about the nature of reality. Let's pull back now to the big picture, to what magnetars mean in the grand scheme of the cosmos, and what they tell us about our place in it. On the 27th of December 2004, a wave of gamma rays swept across Earth. It came from an object 50,000 light-years away, a dead star the size of a city, spinning 7.5 times per second, with a magnetic field strong enough to warp the fabric of space itself. That star's crust had cracked open, releasing energy equivalent to 250,000 years of the sun's output in 1/5 of a second. The wave passed through our solar system at the speed of light. It struck our atmosphere, ionized the upper layers, made our planet's magnetic field ring. It saturated detectors on spacecraft millions of miles apart. It created auroras seen by people standing on Arctic ice. And then it passed, continuing outward into the vastness of space, a ripple from one small corner of the galaxy spreading across the cosmos. This is the universe we live in, a universe where such things can happen, where stellar remnants the size of Manhattan can generate magnetic fields that dwarf anything we could ever create, where space itself becomes a quantum optical medium, where the crust of a neutron star, cracking by a centimeter, releases more energy than our star produces in hundreds of thousands of years. We don't live in a gentle universe. We live in a universe of extremes. Black holes that devour space itself. Quasars that outshine 100 billion suns. Supernovae that briefly outglow their entire galaxies. Magnetars that can reach across 50,000 light-years to touch our atmosphere. But here's the remarkable thing. We're safe. We're far enough away from these monsters that they don't pose a threat to us. The distances are so vast, and the universe is so large, that even the most violent events in the galaxy usually can't hurt us. The closest magnetar is 9,000 light-years away. That's comfortably far. Even if it produced a giant flare tomorrow, which it probably won't, we'd see an interesting astronomical event but no danger to Earth. The magnetars we know about are all far enough away that we can observe them without risk. This is part of what makes us lucky. We live on a stable planet, orbiting a stable star in a quiet region of a galaxy that, while certainly not boring, doesn't happen to have any immediate cosmic dangers in our neighborhood. We're positioned to observe the extremes of the universe without being subjected to them ourselves. And we have the technology and knowledge to understand what we're seeing. We've wondered about the stars, created myths to explain celestial phenomena, used the sky for navigation and timekeeping. But only in the last century have we developed the physics and mathematics to truly understand what's out there. Only in the last 50 years have we known that neutron stars exist. Only in the last 30 plus years have we understood magnetars. The 27th of December, 2004 event would have been invisible to humans. For most of our species' history, we would have had no way to detect gamma rays from space. But in 2004, we had satellites in orbit, instruments designed specifically to detect high-energy radiation. We watched a star's crust crack from halfway across the galaxy, and we understood what was happening. That's an extraordinary achievement of human curiosity and ingenuity. The scientists who've studied magnetars come from all over the world. Brian Gainsler in the United States and Australia, Anna Watts in the Netherlands, Rosalba Perna in Italy, Tomer Shenar in Israel and the Netherlands, Steve Schwartz in the UK, Rachel Stewart and her international team, scientists in Russia, Japan, Canada, France, Germany, Spain, China, and dozens of other nations. They've used spacecraft built by NASA, ESA, Roscosmos, JAXA, and other space agencies. They've observed with ground-based telescopes from the Canada, France, Hawaii telescope to Parkes in Australia to the Very Large Array in New Mexico. They've shared data, collaborated across continents, built on each other's work. This is what humanity can do when we work together toward understanding. We can decipher the behavior of objects so extreme they barely seem real. We can test the predictions of our most advanced theories in natural laboratories billions of times more extreme than anything we could create. We can piece together a coherent picture of the universe from photons that have traveled for thousands of years to reach us. And in doing so, we learn things that matter beyond just understanding magnetars. We learn about the fundamental nature of space-time, matter, and fields. We test quantum mechanics and general relativity in regimes where they might break down, helping us push toward a deeper theory that unifies them. We explore the behavior of matter at densities found nowhere else in the accessible universe. We also gain perspective. When you understand that there are objects out there, natural objects, formed by ordinary physical processes, with magnetic fields a quadrillion times stronger than Earth's, it changes how you think about what's possible. The universe is more creative, more extreme, more surprising than we tend to imagine, and yet it all follows rules. The magnetars obey the same physical laws that govern everything else. The same quantum mechanics that describes electrons in atoms describes the vacuum polarization in a magnetar's magnetosphere. The same general relativity that predicts the bending of light by the sun describes the space-time around a neutron star. The same thermodynamics, the same conservation laws, the same fundamental principles. The universe is comprehensible. Strange, yes. Extreme, absolutely. But not arbitrary, not chaotic. It follows laws that we can discover, understand, and use to make predictions. That's perhaps the deepest lesson of all. Magnetars also remind us how much we still have to learn. For all we've discovered, the list of unknowns is long. We don't fully understand how they form. We don't know what's in their cores. We can't predict when they'll flare. We're just starting to detect vacuum birefringence. We haven't yet caught gravitational waves from a starquake. Each of these unknowns is an opportunity for the next generation of scientists to make discoveries, to answer questions, to push our understanding further. There are students right now, in schools and universities around the world, who will grow up to study magnetars with instruments that haven't been built yet. They'll answer questions we haven't thought to ask. They'll discover phenomena we don't yet know exist. And somewhere out in the galaxy, magnetars continue their violent lives, oblivious to our observations. They spin in the darkness, their immense magnetic fields threading through space. Their crusts slowly accumulate stress. Eventually, they'll crack, sending bursts of radiation racing outward at the speed of light. Some of those bursts will reach Earth, decades or centuries or millennia from now, And if we're lucky, we'll have instruments in place to detect them and learn from them. The universe is vast and old. It was creating magnetars long before Earth formed, long before life arose, long before humans looked up at the night sky and wondered what was out there. It will continue creating magnetars long after our sun has died, long after Earth is gone. These objects are part of the cosmos's natural life cycle, the death throes of massive stars, recycling matter and energy, enriching the interstellar medium with heavy elements, shaping the galaxy's evolution. We're fortunate to be here, now, with the ability to observe and understand them, to catch photons that began their journey when our ancestors were just learning to farm, to measure magnetic fields across thousands of light years, to test quantum field theory using stars that exploded when glaciers covered Europe. This is what we can do. This is what it means to be human in the 21st century in a universe of extremes. We can look out into the cosmic dark, find the monsters that lurk there, and rather than fearing them, understand them. We can see the cracks in a neutron star's crust and know what caused them. We can watch space itself become birefringent and recognize the signature of quantum mechanics operating on macroscopic scales. And as we learn about magnetars, we learn about ourselves, about the elements in our bodies, forged in supernovae that created these objects, about the mathematical laws that govern everything from atoms to galaxies, about our place in a universe that's simultaneously more extreme and more ordered than our ancestors could have imagined. There's a comfort in that. Not in the gentleness of the universe we know now, that it's not gentle, but in the fact that we can understand it. We can make sense of even the most extreme phenomena. We can find patterns, derive laws, make predictions. And that, perhaps, is the ultimate gift magnetars give us. They're reminders of the universe's extremes, yes, but they're also proof that those extremes are comprehensible. That physics works. That human curiosity and ingenuity, given time and resources, can unravel even the deepest mysteries. Somewhere out there, a magnetar spins in the dark. Its crust is under stress. The magnetic field winds tighter. One day tomorrow, or 1,000 years from now, it will crack. A flare will erupt, sending gamma rays racing through space. And if we're lucky, if we're watching, if we have the right instruments in the right places, we'll see it. We'll learn something new. We'll answer old questions and discover new ones. That's the endless dance of discovery. That's the joy of science, the endless frontier, the ever-expanding sphere of knowledge, the profound satisfaction of understanding. So if you've stayed with me through this journey into the realm of magnetars, thank you. I hope you've gained a sense of these remarkable objects, their formation, their structure, their violent lives, their extreme physics, their connections to other cosmic phenomena. I hope you felt some of the wonder that astronomers feel when they observe these objects, some of the excitement when new data arrives, some of the satisfaction when a theoretical prediction is confirmed. And I hope, perhaps, you'll look up at the night sky with a new appreciation. The stars you see are mostly ordinary stars, like our sun, living their long, stable lives. But scattered among them, invisible to our eyes, are the monsters, the neutron stars, the magnetars, the black holes, objects so extreme they redefine what we thought was possible. They're out there, spinning, radiating, sometimes flaring, and we, tiny beings on a small planet orbiting an average star, have figured out that they exist. We've measured their properties. We've tested our theories against them. We've learned from them. That's worth celebrating. If you've enjoyed this exploration into magnetars, if you've learned something new or felt that spark of cosmic wonder, I'd be grateful if you'd like and subscribe. It helps us continue creating these deep dives into the universe's mysteries. There's so much more to explore, from the smallest scales of quantum foam to the largest structures in the cosmos, and I'd love to have you along for the journey. Until next time, keep looking up